Welcome back. In the previous section, we talked about higher order functions, functions that take functions as arguments or return functions as results. And in particular, we looked at two higher order functions over lists, filter and map. And we indicated that these two functions had a very similar structure. They were both defined inductively over the structure of the list. And since we are lazy programmers, we want to capture that pattern into yet another higher order function that we can then use to define filter and map, or in fact, as many functions over lists as possible. That function that captures recursively descending over the structure of a list is called fold_r. Now, there's also a function fold_l. Then what does this L and R mean? Well, fold_r means fold from the right. And just like when we say that the northern wind comes from the north, fold right is a fold that comes from the right. Okay? So it comes from the right, and so it starts with the empty list and then folds from there on. Here is the definition of fold_r. So as I said, fold_r captures the essence of recursing over a list. And what's recursing over a list? Well, we have two cases. Once when the list is empty, and once when the list is composed of a list with a value in the front. So in case we have an empty list, well, when we apply this recursive function, we have to pick a value for the empty list. So let's say that value is v, so f of the empty list is v. Now when we do f applied to x cons x's, well, we recursively call f on x's, that was the whole goal. And now we have to take the result of this recursive invocation and combine it with the value on top. And we use the operator plus for that. So f maps the empty list to some value v, and it maps the non-empty list to some function plus, and applies that function plus to the head of the list, x, and to the recursive call of the function to its tail. So in some sense, you can see what this function f does is it traverses the list and replaces the empty list with v, and it replaces every occurrence of cons with plus. So it remains the structure. So another way to say this is that f is a homomorphism over list. It respects the structure of the list. And that's kind of what we're after here. Now here are a couple of examples of using functions, or of functions that are defined recursively over lists. For example, sum takes the empty list, returns 0, and when I sum the list x cons x's, I do x plus the sum of x's. The product is very similar. Instead of 0, I have 1, and instead of plus, we use star. And if we want to AND all the values of a list, well, then we replace the empty list by true, and the cons by AND. Okay, so here you see very, very similar structures. And in particular, we can instantiate v and plus very simply. In the first case, the empty list v is replaced by 0, and cons, that was the funny plus, is plus. In the second case here, we replace the empty list by 1, so v equals 1. We replace cons by multiplication, so the funny plus is times. And in the last case, simple, we replace the empty list by true, so v is true, and we replace cons by AND, so funny plus is AND. All right, so here we can define some product or an AND in terms of fold_r simply as fold_r of plus and 0, product is fold_r of times and 1, etc. Okay, so look what we have done. We looked at these three functions, and we see that these are just instances of this fold_r function with a particular v and a particular plus. Okay. Now, how do we define fold R, because we defined this pattern here, so now we have to define this thing itself as a higher order function, okay? So we have to have a function that takes f and v as parameters and then, captures the recursion. So here's the definition of fold R as a higher order function. It takes first an operation that replaces cons, so that's a function of type A arrow B arrow B. The second parameter is v, that's the function that we are using, or the value that we're replacing the empty list with, and then we get a function from list of A to B. And the definition here is straightforward. Fold R of f and v and the empty list, that was a v, and fold R of f and v and x cons axis is the recursive invocation of fold R of f and v, and then we call f on x. So instead of the funny plus, we use f. All right? But even though, you can look at this definition, this recursive definition, the easiest way to think about fold R is, as I said, is a function that replaces everywhere the empty list by v, and it replaces the cons operator by f. You see? So everywhere where you see empty list, it becomes v. Everywhere where you see cons, it becomes f. Okay? So, and then it just goes recursively like that. For example, if we evaluate sum of 1, 2, 3, sum is defined as fold R of plus and 0 of 1, 2, 3. Now we expand the definition of lists. We know that 1, 2, 3 means 1, cons 2, cons 2, cons 3, cons empty list. And now you see, again, why the syntactic sugar for lists is so useful, because this would be very tedious to write. We don't want to write this all the time. So I'm super happy that Haskell has a shorthand for lists that expands into this. And in this case, we have to kind of think about it a little bit. And now what happens is that we're going to replace every occurrence of cons by plus, and every occurrence, which is one occurrence, of the empty list by 0. Let's do that. So it becomes 1 plus 2 plus 3 plus 0. And you see, the structure of the list is maintained. Fold R is a homomorphism over lists. The structure is still the same. It just replaces the constructors by another function. If you're familiar with the visitor pattern, fold R is really very similar to the visitor pattern. It visits the list, and for every constructor, it applies a function. And that function is passed as the parameters to fold R. And if we evaluate 1 plus 2 plus 3 plus 0, the result is 6. Now, it's kind of obvious what happens with product 1, 2, 3. We go to the same derivation. Product was defined as times 1, 1, 2, 3, 4. 1, 2, 3. We expand the list. We replace every occurrence of cons by times and every occurrence of the empty list by 1. We evaluate this expression, and the result is 6 again. Good. Now let's look at some other examples of fold R. For example, the length of the list. We can define the length of the list, function that takes a list of A for all types A and returns an int. The length of the empty list is 0, and the length of the list x cons x's is 1 plus the length of x's. Now, Haskell programmers are lazy, and since we're not using x in the right-hand side here, we just use an underscore for x, so we don't have to think about a name. Okay, so we remember the underscore. When we use that, it really just means this is a variable, but we're not going to use that in the right-hand side. Well, it's obvious here that length is another instance of fold R. We're replacing the empty list with 0, and we're replacing cons with the function that throws away x and then adds 1 to the recursive invocation of fold R on the list. So let's make this explicit. So we do length of 1, 2, 3. That's the same as length of 1, cons 2, cons 3, cons empty list. That's the same as 1 plus 1 plus 1 plus 0, which is 3. So if we replace cons with the function lambda underscore n, 1 plus n, and the empty list by 0, we get exactly what we want. You see? So cons is replaced in this step here by the function that throws away the first argument, so we don't write it, and then it takes the second argument and adds 1 to it. So you see exactly that is what happens in that step. So what we have found is that length can be defined as fold R of lambda underscore n, 1 plus n, and 0. Let's look at another example. Reverse. Reverse of the empty list is the empty list. And reverse of x cons x's is reverse of x's append with the singleton list of x. And by now, we should be trained to see this pattern, right? We see two cases, the empty list and the list x cons x's. And on the right-hand side, we see that function, reverse, applied to the rest of the list, plus some function, involving x that we apply to the result of this recursive invocation. Okay? And in this case, the reverse is a little bit tricky because, the recursive call appears here on the left instead of with length where it appeared the recursive call. Let's go back to length here, where the recursive call appeared on the right. But this won't fool us. That's just simple. No worries. So let's look at reverse. Reverse 1, 2, 3. Again, that's the same as reverse 1, cons 2, cons 3, cons empty list. Which is the same as empty list concatenated to 3, concatenated to 2, concatenated to 1, which is 3 to 1. So what function are we using to replace cons, and what function are we using to replace the empty list? Okay, so you see here that things are reversed, but that shouldn't fool us, because we see here that the parentheses are right. So we are doing something with 1 and the recursive call. The fact that, this is reversed, that is not important, okay? So if we replace cons with the function x's goes to x's cons x, so there you see that it's swapped. The x appears to the left here and to the right here, and we replace empty list with the empty list, then this all works out. All right? So we can define reverse as fold R of this function, where we replace cons by the function cons, which takes a value and something else, and we put x to the right, because we're reversing the list, and the empty list is already reversed. Okay. So now, if we write this in point-free style, we can write this a little bit shorter and write it as, the appending y's to the end is the same as folding cons with y's. All right, so if you want to append a function, if I want to append a list, I'm just replacing the empty list by that list, and I'm leaving all the conses alone. Okay, so why is fold R useful? Well, many recursive functions on lists, such like some product and or, are quite simple to define using fold R. We have seen length, which was a little bit harder, and reverse, which was even a little bit harder, but still very simple. Now in the exercises, you will have to define map and filter in times of fold R. So we leave that to the exercises, but since you have seen these examples, that should be easy. But the nice thing is that we can define properties of fold R such as fusion and the banana split rule. That's why I was eating a banana earlier on. And we can use these properties to calculate more efficient programs. In particular, fusion means that I have two functions, one that kind of use fold_r to kind of traverse one list and return another list. And if I do another fold_r on the result of that, I can fuse these two together such that the intermediate list is never constructed. So programs can be optimized if you write them in this higher order pattern. Okay, so don't forget to do the exercises. Part of them will be to define map and filter in terms of fold_r, but by now that should be easy, and you can do that while you're enjoying a nice banana. Thank you, and see you next time.